Hello everyone, this is a presentation of data mining project for University of Oklahoma, fall 2017, Group 4 group project, which is called GitHub Repository Success Prediction. So our application is mines data out of GitHub logs, which are available through GitHub Archives website. It pre-processes them and converts them into a data set which has two main tables we use after that. So you have a contributor table with ID, timestamp, and a lot of counts for what events could have happened related to that contributor and events they were producing for that week. So our data is sliced and aggregated in weekly time periods. So for contributor, we record events regarding creation and forking of repositories, code pushes, pull requests, and issues activities. For repositories, we record number of stars, number of total contributors, code pushes, pull requests, forks, releases, and other activities. Also, we have reserved 5 fields of different contributor types, which are not originally populated but are backfilled when we cluster our contributors. So let's start with basic idea of our application is to first run clustering of our contributors, populate these 5 reserved fields in repository table, and using all this data for repository basically predict how successful repository will be over some period of time. So let's start with demonstrating. So we developed 2 different algorithms for clustering of data, for clustering of contributors. We have k-means clustering and we have hierarchical clustering. Let's try to so we will be using a much smaller chunk of contributors. We will only use a sample of 1,000 contributors. Our full data sets contains 20 million of them, but for reasons of saving time, we will only be clustering a small chunk of that just to demonstrate how things work. So it appears our application consists of basically 5 scripts. First script is for running pre-processing. We will not be demonstrating it as it takes a long time, and our original data set being so large, we had to run pre-processing on University of Oklahoma supercomputer here. Big thanks to those guys for lending us that resource. So let's consider our results. It appears that we got 5 clusters, which is exactly how many we asked for. And those clusters, basically majority of contributors landed at cluster number 5. We have another one, somewhat big, and the other guys are small. This result is not terribly surprising because, as it turns out, after we did our data exploration, majority of contributors are dormant over time. So this algorithm produces 5 clusters for us with respective centroids. So we have 10 different parameters we use for clustering of our contributors. 4 of them related to issues activities, 3 related to code pushes and pulls, and 3 more for creation of repositories. If you want to know more details about which one's which, you will have to go ahead and read our report to figure that out. Now let's move to the alternative clustering algorithm, which is a hierarchical clustering. Let me fetch a command line for that. Okay, it seems to run, something happening. So let's, again, we're using a small sample of 1,000 contributors. We will cluster all of them, which is somewhat an interesting point for hierarchical clustering, because it uses O(n) square of memory, so number of contributors we can actually cluster cannot be very large. So once we cluster that sample, we actually doing so-called modeling of other contributors in our dataset by one-to-one adding them to existing like dendroid for hierarchical clustering and seeing which of the cluster that new contributor will join. So it's not clearest of clusterings, but it actually allows us to process our whole data set. So it looks like our algorithm managed to build initial proximity matrix. It managed to merge the clusters until the end, and now what it's actually doing, it outputs clustering of all contributors and save them into SQLite3 database, which our regression algorithms will later use. So now it looks like this algorithm produced just 3 clusters, and it appears that all of them are populated. Biggest one, again, taking 74% of all contributors, as you can see, contains 0 or close to 0 values. Those are basically dormant contributors, but we also have 20% chunk of whole sample cluster which contains contributors which are moderately active, but there is also like 5% cluster of contributors who are quite active. So this is our hierarchical clustering. So results of our clustering are used to basically produce mapping in our databases from contributor ID to cluster ID. Now let's actually see how we can use those results, and let's try to run logistical regression. So we start our regression with training a model on a small sample of repositories, and I will actually hand you guys over to Timo, who developed this algorithm. Or rather, I will let Timo interpret results of the algorithms, and I will keep launching them myself. So first we will train our regression model on relatively small samples of repositories. Let's see how that works. Not very well. Windows shell does not like me.
We already know that this sample will not give any good results, because as Taras already said, most contributors are dormant and most repositories are too. We have a very sparse data set. Most elements are just zeros, and so the vast majority of repositories is not going to be active. Just about 1 in 3,000 is going to be. And so the 100,000 repositories dataset is just too small to get any significant results. But for demonstration purposes, we're going to use it anyways. So we see here that we did 3 rounds of logistic regression. That's because logistic regression works on the Newton principle of finding or approximating a local minimum. We converge on that minimum in 3 rounds and can see here that we got our coefficients for our parameters that we chose. Those are a bunch of averages of the repository. For example, the average star count in 1 week, the average code pushes, etc., as well as deltas, which means the amount the starings changed in the last 2 months of the record, and the same for pushes and PR created. And here we could, for example, see that the average pushes very significantly determine whether the repository is going to be active or not in half a year. Whilst, for example, the contributors of type 1 would actually decrease the likelihood that the repository is going to be active in half a year, which might be, if we want to interpret something into this, but as I said, it's not really meaningful, which might mean that those contributors are those that are not producing any good code or something like that.
For the actual real result of this modeling, you will have to check out our report as usual. Now we can take a look at what kind of model our algorithm produced. That would be just this thing. So we have a vector of coefficients, right? And those coefficients determine how successful a repository will be in the future. And again, you at this point know what those coefficients stand for in general. For specifics, again, please check out our report. Now let's move along. Now we can predict basically the activity of a certain repository which is a member of our small sample of data based on the model we produced. Let's see what we get here. Alright.
Now, as we see before, our model is really meaningless. We have a total accuracy of 0.1% when we take 90% for training and 10% for test. So here we have a repository that is actually not doing anything, as we can see in the record, but the model says it's true anyways, because that's what it says for every record besides 6.
But we also can run our model, can evaluate the artificial repository using our model. So let's do that. Looks like our artificial repository will not be active in half of a year. Well, maybe this model knows something. Alright, I think that's it for our logistic regression, and now let's try the different regression we developed, which is linear regression. So this one, again, we will be running on a small sample of data, 100,000 repositories, and let's see how it works. Alright, so we got some results, and I will let Jasmine, the author of this algorithm, interpret them.
Okay, so as you can see, we have the average value, which is the average predicted value for the points, and as you can see, it's negative. So that means that it would not be successful, seeing that it will continually be negative and go down. Also, we have the coefficients, and the coefficients to help pick the independent variable and how it varies. So if you can see, some of the numbers are like 70.94 and 10.86, and the smaller numbers shows that the variance is really small. And last, we have the error measure, and the error measure shows how far that it is away from the line. So if you can see that it is 5.84, that means that the error is 5 units away from the line.
All right, sounds good. So also, as you can tell, providing a graphical user interface for our project wasn't the first priority, but nevertheless we did some work on that. So let's launch our web server and see what happens. Looks like our server has launched. Let's check it out on a local host. Alright. So we can do 3 things from our UI. It's not very fancy, I know. So we can pre-process our dataset, we can apply it to our clustering algorithms, and we could classify one of the repositories using the model which we calculated before. So unfortunately we were pretty short on time and not everything quite done here and not quite everything connected together. But at least now we can show you results of hierarchical clustering. Again, UI is pretty bad. And basically it tells it basically takes command line arguments of our script and it passes them to our server and returns a result. Yeah, so that's a result which we similar to what we've seen before, but in this case we processing like a very small cluster of 100 contributors, and in this case algorithm chooses to stop when having 5 clusters, meaning that if we move to 4 then our error will increase by at least 10%. So yeah, unfortunately at this point this is all the UI we've got. Additionally, let's try to demonstrate how our classification logistic regression works for our algorithm. So first let's try to classify the same repository we were classifying from our command line.
The difference is that now it's classified not by the model we built earlier, but by a proper model built on the whole dataset. So now that one has a high accuracy of over 99%. So now it actually recognizes that this record will not be active.
Now let's try plugging in the repository ID, which we know contains some good signs of activity, and see what happens.
Yeah, this repository actually contains some activity, some out of the norm high activity, and it's obviously because of that going to be predicted as active. And you can also enter a repository manually by just entering values into the below fields. You can try that by just entering any values in case you want to fill with the parameters to find out what you need to adjust to make your repository more successful. You can try that here, and it will tell that this repository will not be active. Bad news.
For some reason. Alright, I think this concludes our presentation. Thank you for your attention, and have a good luck and good holidays. Bye!